Okay, we are recording and we're continuing our talk on evolutionary sort of stuff. I want to be talking today about straying a little bit from electrical and computer engineering and literally talking about things such as Darwinian evolution and the debate about Darwinian evolution. And I'm going to present one side. There is a debate coming up this Thursday at the Herd Center, and it's between a somebody that purports to believe in a young Earth creationism, and then there's old Earth intelligent design, and there's old Earth Darwinism. So if you'd like to hear all three sides, that's a good place to come to. And I'll give you the specifics on that at the end. Okay, so with that, let me go ahead and share my screen and go ahead and start the lecture. Here's what we talked about before. We talked about something published in, I believe, 1989 by Wolpert and McCready called the no free lunch theorem. The no free lunch theorem says if you have no domain expertise about a search, if you're trying to search for something, then you got a problem because one search on average is about as good as any other search. We talked about, for example, an assisted search wherein somebody told you were getting warmer or colder, and that was actually active information. So we actually talked about the blind search where this guy was with the Rubik's Cube sitting on a bench and going, is this it? No. Is this it? No. Is this it? That was a totally blind search. It was totally just a random search. Sometimes the random search is actually very good, and it's better to do a random search than it is to look at the history of the search and to do something according to the history of the search. Um, we talked about getting warmer, getting warmer. You can tell people you can assist in the search with domain expertise because you know where the target is at, and you get warmer and warmer. And that's okay, but you could also get a case where you're getting colder and colder, and somebody could lie to you, and that's also somebody giving you advice. That's another oracle. Now, does it ever work that it's getting colder is actually a viable way and will help you get to the result, even though you're being lied to? Yes, indeed, that is the case. And hopefully, we'll get a chance to show you that there are searches where if the oracle lies to you, you actually have a better chance of getting the result. So we talked about the needle in a haystack, the idea that the no free lunch theorem says on average, this is a big thing, on average, one search is as good as another search if you have no domain expertise. So we did talk about getting warmer and getting colder. You can say warmer, you can get colder. And that will help you if it is an accurate oracle, but you can't choose your oracle at random because sometimes an oracle that lies to you will actually do better. Um, and then there's the Hamming oracle. The Hamming oracle is a little bit smarter. All of these oracles have relative degrees of smartness, and the Hamming oracle is even smarter than the getting warmer and colder because the Hamming oracle basically says how near you are to the solution. It turns out that in most searches, you apply your own domain expertise in order to assist the search. And your domain expertise hopefully is accurate, and the accuracy is um, the accuracy of your domain expertise is paramount. So one of the things that I did with a guy named Bill Dembski is we actually went into the no free lunch theorem, and we looked at how we could measure the amount of information that was added to a system in order to make it work. And that would be the so-called active information. So it turns out that a lot of evolutionary programs are pre-wired in order to get you success. And that pre-wiring comes from domain expertise, and this domain expertise, the degree that which it assists you in the search can indeed be measured. And this is the paper that we did, Conservation of Information in Search, Measuring the Cost of Success. And we coined the concept of active information, which is the amount of information that we add to the search. We talked about this last time. Let me review it. Here is I guess it's 10 bits. So in order to crack this combination, you have to do 10 bits. So that's one chance in 10,000 or 1,024. But if you have somebody come to you with domain expertise and say, you know what, the last three bits are 101, then all of a sudden the difficulty of your search is decreased by a factor of 248, I think it is. So the domain expertise is important. This is an obvious case, but there are other cases which are less obvious, which we'll talk about. We talked about the idea of random search and the help that you have on random search, and we went through some examples of that last time. And we looked at different ways of doing it. Unassisted random search would run forever. It would run forever, and not forever, but I don't know until the sun explodes or something like that. But then if you give it some sort of information about in order to make it converge to the correct answer, like you're getting warmer or whatever, um, you're going to um, you're going to get better and better, and you get better results. And you can do this either with the evolutionary search, where you have a number of offspring. This is the case, for example, of the proximity reward search. Methinks there was actually 15 offspring. So we had 15 offspring. We actually computed the Hamming distance. The Hamming distance was used as the measure of success, and then the mutation rate. But notice that something is happening here. In order to get the Hamming distance, what do you need to know? You need to know your target. You need to know where you're going. And uh, evolution normally is presented as undirected random search in order of mutations. And that simply doesn't work. So let's talk about the cost of success. The cost of success, if you have n letters in the alphabet and the message is L letters long, okay, n letters in the alphabet. Now n is going to be 27. That's going to be 26 letters plus a space. So we're going to make it easy. We're not going to use lowercase, just capital case. We're not going to use any numbers. We're not going to use any punctuation. We're not going to use any weird symbols like a pound sign or a percent sign or a question mark. Just 27 letters. Now, the number of bits per query is the log base 2 of n to the L. This comes from information theory, and this is your cost in bits. And we can also figure out the number of queries that's required. It turns out that with a oracle that we have what we call a Bernoulli trial. And the Bernoulli trial is either a success or a failure. You have a success or a failure. That's a Bernoulli trial. It's a Bernoulli random variable, and it's something we can actually assess the expected number of queries that are going to be that's going to result. So the number of queries on the average, the number of bits that is required for a search is this number. This is the number of queries times this number, which is the number of bits per query. Now, there's some people that separate this into, for example, they separate the idea of the number of queries and the number of bits per query. But let's just, for fun, put them together, and we get n to the L log base 2 of n to the L. And so this is the number of bits required for a search of a English phrase like "methinks it is like a weasel." So if we apply methinks it is, if we apply this formula like we think methinks it is like a weasel, L is equal to 28 letters in the message and N is equal to 27 letters, that turns out that the number of bits we need is 1.2 times 10 to the 42nd. That's a million, billion, 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 billion bits. So that's a lot of bits. So that's probably prohibitive. So this shows that the blind search, which is on average as good as any other search, is simply prohibitive in terms of a search for this particular target. Don't forget, every search is different. Every search is going to have a different outcome. So let's go ahead and let's think big, and let's think about numbers which are really big in terms of number of bits. Here's what I'm going to do. We're going to just think big, and I want to get a big number. I want to get a number bigger than the universe, bigger than the multiverse, and talk about this number and ask how large of a sentence that we can search for. Now, let's talk about a cubic Planck volume. What's a Planck volume? Well, Planck length is, or the Planck length is probably the smallest measurable value that there is. And one Planck volume is equal to a Planck length on three sides. So we make a Planck cube. So it turns out that if we want to look at the area of a Planck cube, that's, as you see here, 1.7 times 10 to the minus 104th. Now, this 10 to the minus 104th is incredible. If you look at, for example, the number of protons in the universe, I think it's 10 to the 82nd or something, somewhere around there. So this is monumentally small. Now, the Planck volume is so small that ah, it is incredibly small. Suppose you took a Planck length and you scaled it to an inch. So you take a Planck length, you scaled it to an inch. Then diameter of a proton, the diameter of a proton would be several light years across. Think of that. If you took a Planck length and increased it to an inch, the diameter of a proton, an estimate of the diameter of a proton, would be many light years across. I mean, that's just astonishing to think about. And this is one of the reasons that string theory hasn't really caught on, is because string theory has to look at things, as I understand it, I'm not an expert in it, but string theory says that you got to get down to, say, a Planck length in order to evaluate the theory of string theory. So string theory has been around for a long time, but nobody has any experimental results because you got to get down to the Planck length, and you can't do that. So that's a lot of numbers. Okay. What is Planck time? Planck time is the time that it takes light to travel a Planck length. The time that it takes light to travel a Planck length. Wow. So that is really small. Since the Planck length is very small, the time it takes light to go that distance is also very small. And it turns out that's 5.39 times 10 to the minus 44 seconds. That's pretty fast. So what we're going to do is we're going to take the Planck volume, and we're going to do the Planck time units, and we're going to assume the universe. What is the universe? We're going to take the volume of the universe in Planck cubes, and then we're going to assume the Big Bang, and we're going to talk about the time since the Big Bang in Planck time. So if we look at all of the Planck cubes in all of history divided up into Planck times, we get 10 to the 244th. So again, the universe is divided up into Planck cubes, and it's divided up, and the history is divided up into Planck time units. And it turns out that this gives us 10 to the 224th Planck volume times Planck time units. Now, this is not bits. I'm just trying to get a really, really big number that if we play around with this number and it can't do anything in terms of blind search, that we can say, well, that blind search is not going to work. So let's look at this. We're going to assume that we have 10 to the 244th bits. That's the number of Planck volumes times the Planck time units since the creation of the universe. And you notice this is a transcendental equation. In other words, n we know is 27, and we're not sure what L is. So we have to do a search, if you will, an interval halving or some other sort of thing. It's a transcendental equation. So we're given the number of bits, 10 to the 244th. We're given n, which is 27, and we got to figure out what L is. If we do this, it turns out that we get something like 169 characters. I want you to think about that. 169 characters. So we can only generate by blind search phrases of the length 169 characters. So to give you an idea how long that is, the Lord is my shepherd, I shall not want. He maketh me to lie down in green pastures. He leadeth me beside the still waters. He restoreth my soul. He leadeth me in the path. And then it stops. That's 169 characters from the alphabet, all capital letters, no numbers, no punctuation, no question marks or hashtags or anything of that sort. So that is an astonishingly short time. So blind search does not work. So anytime you hear somebody saying that a search is random and undirected, you have to keep this in mind. Now, those that say, well, maybe there's parallel universes. Well, let's talk about parallel universes. There's many theories of parallel universes, but one of the most common models says that there's 10 to the hundredth to 10 to the thousandth parallel universes. These are universes which lie in, say, a higher dimension parallel to ours. And there is absolutely no proof of parallel universes. But let's give the benefit of a doubt. There's only speculation. So you add exponents when you multiply numbers of this sort. And so we get 10 to the 1244th. So if we had 10 to the 1244 bits, how long a phrase could we search for? Remember, these are the Planck cubes, the Planck time since the beginning of the universe, the Planck cubes at every instance of Planck time in the universe, and that's 10 to the 1244. Well, we could get only 867 characters. Wow, I think that's really astonishing. And that's and if we compare this, for example, to Lincoln Short Gettysburg Address, it only contains 1,422 characters. So we could not even get a search for the Gettysburg Address. Now, Eric Holloway and I have recently published a paper where we actually looked at the case where we weren't looking for a specific address. We were looking, or a specific phrase. We were looking for any meaningful phrase. What's the chance of generating any meaningful phrase? And we looked at the length of meaningful phrases that we could talk about. Now, what do we mean by a meaningful phrase? Well, we were really sloppy in our definition of meaningful. Our definition of meaningful phrase is a phrase containing any words in the dictionary. So they don't even have to make sense. They don't have to make any logical proposition at all. It's just words selected randomly from the dictionary. And we showed that the results were not that great. And the increase is not that much. In fact, it's about the same. We published the work in the book Minding the Brain. And if you're interested in actually looking at the results of that, it requires a lot of information theory. But if you look at this result, you'll find out that yes, indeed, that even relaxing it from a specific phrase to any phrase with meaning, a phrase of meaning any string of characters with words from a dictionary. And even that, it doesn't work very well. I think it goes down to maybe 100 or 700 characters or something of that sort. So therefore, the blind search does not work. And this gets us to the point of a famous a famous scene from Dumb and Dumber. So if people say that you're going to use random search in order to generate something, this from Dumb and Dumber should be the reason.
I want to ask you a question straight out, flat out. I want you to give me the honest answer. What do you think the chances are of a guy like you and a girl like me ending up together?
Well, Lloyd, that's difficult to say. We really don't...
Hit me with it. Just give it to me straight. I came a long way just to see you married. Just, least you can do is level with me. What are my chances?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of 1,000,000.
So you're telling me there's a chance? Yeah!
Okay, that's a classic scene. So if you believe that you could actually generate phrases or generate meaning from random searches, it ain't going to work. That's just like Lloyd Christmas. I don't know if you've ever noticed, but he was courting a woman named Mary Samsonite. He thought her name was Mary Samsonite, and if they did get married, since his name was Lloyd Christmas and hers was Mary Samsonite, her name would be Merry Christmas. I think that that was kind of a hidden Easter egg in Dumb and Dumber. Merry Christmas. Okay. Now, there's something called Burrell's Law, and that's when the improbable becomes the impossible. And let's talk about this. There is a chance right now that you will do quantum tunneling through your hair. I asked Professor Olafson this. She knows about quantum stuff, and she said that yeah, there's a chance, but it's really really small. So think about the idea of, I don't know, maybe choosing one of the atoms in the universe, 10 to the 83rd atoms. You choose one at random, and I choose one at random. What are the chances that we choose the same atom? I would say, yeah, there's a finite probability, but the probability is so daggone low that that improbable becomes literally impossible. It's simply never going to happen. So understanding that any sort of evolutionary search requires information um, got our attention to this paper, Evolution of Biological Information. This was a guy from NIH, and he said he was excited because he had a computer program that showed evolution. And the thing is that, yeah, in the 1950s, all the biologists got excited because they say now that we have computers, we can literally do wonderful things because we can simulate evolution on a computer. And is this is something which people have tried, and unfortunately what they do is they make the evolution work, but they sneak active information into it. They guide the results in order to get to the final result. So we wrote a response paper, a vivisection of the EV computer, identifying sources of active information. In other words, where were they sneaking active information? It turns out that Schneider was indeed using a Hamming oracle in his search. So he was really supplying a lot of information in the search, and we showed this and actually was able to measure the active information that he put in to make his evolutionary program work. So if evolution, Darwinian evolution, has a Hamming oracle, yeah, maybe it'll work, but I don't think it has a goal. So here we are at EVWare, and there's a number of different ways that we can do it. One of them is to do the EV binding sites. And let's just go ahead and start it. This is EV search with 64 organisms. There was only one mutation, and the survival is 50%. So in other words, we killed off the 50% weakest, and continued. So let me start the search. Now, what you see here on the top is the goal, and on the bottom is what we got. I'm sorry, it's just the opposite. On the bottom is our target. On the top is what we would like. So you see down here in the bottom left that they match. So this is a very good search, and this is working very, very well. So this is EV search. This is actually applying the algorithm that Schneider had. And you can see every once in a while a new one clicks in, and we're getting better and better as ones appear on top of other ones. That means that site has been evaluated. Okay, here is another search. This is EV search, but we can choose other searches, and you could do a number of them at one time, but the screen only can allow us one of them. Let's do one for this is called a ratchet search. This is something called stochastic hill climbing. What we're going to do is we're going to make a change. If the changes get you to be better, then you keep it. If this change is not good, you go back, you revert to where you were before and try another change. And that's a ratchet search. So you're ratcheting to make sure that your fitness either stays the same or increases every step. So let's see what happens with ratchet search using Schneider's original binding sites of 1. Actually, this works a lot better. And I want you to notice that there's literally no evolution occurring here. This is one organism that we are looking at. This is one organism that we're looking at. And so we can see that the ratchet search is continuing to do its thing. And don't disappoint me, ratchet search, because I think you should be doing better. Okay, we don't have a match yet. Okay, well, have I started the search? Okay, we're going to do a different target. We're going to do random binding sites. In other words, just have a bunch of ones and zeros as our target chosen at random. We can do this also. And you can see that we want to match the bottom and the top here with the ratchet search. If it gets better, that's good. So the ratchet search is knocking it out of the park as it identifies all of the ones and zeros associated with the original target. By the way, the ratchet search uses the idea of a Hamming oracle. In other words, are you getting better? Is your Hamming distance decreasing? If it is, the Hamming distance is such that we keep that result. If it doesn't get better, we go back and revert to our original result and try something else. Now, it does turn out that this Hamming search has diminished results as you increase. Why is that? Because as you get closer and closer, as the Hamming distance decreases and you get smaller and smaller, it should be obvious that the chances of you finding an erroneous match become smaller and smaller because the number of erroneous matches have decreased significantly. So if you actually looked at the curve, the statistical curve for this sort of search, you would find it's a lot like a capacitor charging. It's a kind of a 1 minus e to the minus x. And so as you get closer to the result, you get more and more difficulty in identifying targets that don't match. Now, there's something you can do and keep a history of all the targets you looked at, and that's not done here. That's not done here. So, so you see, we're taking a long time to make different results. Okay, so all of this is on evoinfo.org, and you can take a look at it if you so desire. So this is our result about the vivisection of the EV computer and identifying the source of active information. The fact that they were literally using a Hamming oracle. There was another one, and this was a bigger deal. This was the Evita program. This was a evolution project funded by the National Science Foundation, and it included Richard Lenski. Now, Richard Lenski is a biologist. You can see he's with the Department of Microbiology and Molecular Genetics. And one of the things that Lenski tried to do is actually simulate biological evolution in his lab. He took vials and vials of many, many E. coli bacteria and subjected them to different results, not different results. He subjected them to different environments, trying to force an evolution. And it never worked. And he kind of abandoned it, but they said to come back and try it again. Everybody was saying, well, you just haven't waited long enough. Now, here is the Rube Goldberg machine. I don't know if anybody remembers the Rube Goldberg machine. These were machines where you drop a baseball onto a lever, and this lever is on a seesaw, and the seesaw, the other end, pops up a cube, and the cube scares a cat. And the cat runs over and knocks over a bottle of perfume, um, and the bottle of perfume starts to spread out. And since it has alcohol in it, it causes a short circuit that activates something else. So it's just a long, complicated way of doing things. And this was the result from Evita, and this was the picture that they had in their book or in their paper. Just very, very complicated. But here's what they were doing. I don't know if you know this, but all of the logic operations in the world can be done with NAND gates. In fact, there used to be chips which were made totally out of NAND gates, and you could do any logical operation using NAND gates. And here's an example. Uh, so up in the left-hand corner, you can do the NOT by shorting the input together. You can do a NAND gate. You can do an AND gate by cascading two of these. And you can do an OR gate. You can do, well, this is called, oh, no, I guess this is called an OR. This is called an OR-N, a little bit different. It takes the original input and ORs it with the complement of Y. And then all of these other logical operations, okay? And then we have an exclusive OR down here. Now the exclusive OR takes 4 NAND gates in order to operate. And then there is the XNOR gate. And the XNOR gate is the most difficult to implement using NAND logic because it takes 1, 2, 3, 4, 5 different NAND gates in order to do the XNOR. And this is called, in the paper, is called the EQU. This is their goal. They want to evolve this. Now, notice in doing this, they're actually using previous results to help them do stuff. Like, for example, we have the AND gate here. Well, the AND gate is using a NAND gate, and it's using a NOT gate, right? It's using an AND gate and a NOT gate. And so these have been implemented already in steps 1 and 2. And similarly with the OR-N and the OR is using the NOT gates here and the AND gates. So once you develop the NOT gate and the NAND gate, you should be able to do, if you stick them together right, you should be able to do an OR gate. Well, and then we get the and then the XNOR, I think, is the most easily seen because the NOR gate does what? It takes the OR gate and it slaps on a NAND gate or a NOT gate at the back, and you get a NOR gate. You have the exclusive OR, and then you get the XNOR or the EQU. They call it, in Avita, it's called the EQU. And you'll notice that the EQU uses the logic of the XOR gate. So therefore, what they did is they decided not only to choose as a goal the XNOR gate, but they were going to use as stepping stones by giving different values of fitness for when you got a NOT gate, a NAND gate, an AND gate, and all of these gates, which were kind of built on each other. And here is kind of a picture depicting that. This is getting to the EQU or the XNOR by climbing up the stairs of the NOT, the NAND, the AND, the OR, the AND, the NOR, the XOR, the EQU. And in order to get there, you have to go up these steps. These steps were provided by the Avita program, believe it or not. So not only did they have a goal, but they sketched out a path in order to get there. This was, by the way, the Avita program was refinanced by NSF to be a program which was used to illustrate Darwinian evolution to high school students. And that will become very interesting. So there wasn't a stair step. If you didn't have a stair step, then getting from the bottom to the EQU would be one enormous step in information. And it wouldn't work. It wouldn't work. And indeed, that's what they found out, and they admitted so in the paper. They said we started the population with 3,600 different organisms. In other words, that's how many were in their brood that they mutated and generated a fitness function for. And each one was 50 instructions long, and 15 were required for efficient self-replication. The other 35 were tandem copies of a single no operation instruction. And the case study was one of 50 that evolved under identical conditions. So it turns out that many of their random evolution things turned out to work. And they admitted that. But then they came along and they admitted something else. They said at the other extreme, if we had 50 populations and supplied no stair steps, then the evolution didn't work. Well, duh, because it's a random search. Is this it? No. Is this it? No. Is this it? No. And eventually it would work, but it would require lots of different steps, maybe more steps than existed in the universe. There was a famous trial in Dover brought on by Kitzimer, which looked at whether or not intelligent design should not be taught in a school, but whether when Darwinian evolution was taught, that there was an admission that there were other perspectives in this. And Pinnock was one of the co-authors of the Avita paper, and he said one of the things that we use ourselves in evolution of computer organism programs is such as Avita, is that you can have a system in which you have self-replicating computer programs that continue to mutate and to vary. And in that environment, you can get what we call logical function evolving. Logical function being, of course, the concatenation of the NAND gates. For example, you can get a simple logic gate, it evolves. Then you can get a more complex logic gate and so on. What this shows is that under certain conditions, you can see successive changes in functional computational systems. But the crucial point is that what you get are changes within the parameters of the system that's been set up. You do not get the kind of novel biological relevant complex structures that the intelligent design movement claim are problematic for Darwinian evolution. Then he said something sort of remarkable. This was under oath at the trial. In the Avita system, we're not simulating evolution. Evolution is actually happening. So if evolution is happening, that means that there was a designer which came in, gave the stair steps in order to get to the elevation, if you will. And it wasn't undirected random mutation and Darwinian evolution as it is presented. It was structured. There was lots of active information that they snuck in here, and we can see this. So we debunked this in a paper called The Evolutionary Synthesis of NAND Logic Dissecting a Digital Organism, and we're able to measure the active information associated with it. So I want to show you some very interesting software, which was written by Winston Ewart. He's the first author on this paper. Dr. Ewart was my student, really brilliant guy, and he he blew away other programmers. He was frankly astonishing. So here is what it is. This is Mini Avita. Mini Vita. This is at evoinfo.org, and it actually shows the evolution of a computer attempt at solving the Avita problem. Okay, first of all, we have to choose the tasks. These are the stair steps, and this is the amount of credence that the stair steps are given. So the amount of fitness. So you want to increase the fitness. So the NAND and the NOT, which we saw were the elementary versions, were given an assignment of 1. The OR, IN, and were given a value of 2. And a couple of them were given 3. The NOR and the XOR were giving 4. And then the final one was 5. So the number of the degree of success, the fitness of each individual was scored by how many NAND gates that it used constructively. We have instructions. We're going to use all the instructions. They had 26 instructions, 1 for each letter of the alphabet. Go figure. And then the settings is, of course, it's an evolutionary search. So what do we do with the population size? And we see that we have this result here. Okay, here's the situation. We set the tasks, we do the instrumentation, and we go to the simulation. Now, the simulation actually shows the best result as a number of iterations. So let's go ahead and reset this and run it again. And what you can see is the circuitry that is generated by the Avita algorithm. And sometimes it doesn't work. Sometimes it doesn't find a solution. And by the way, you can see this genome over here. These are the letters from A to Z, which show you the different steps that you have in this Rube Goldberg machine. And there you see that we indeed have it. So this is after 569 iterations. This is 58,000, or no, 589,000 iterations. And you can see that it did it. So let's reset and see if we can do it again. I believe this is brilliant programming by Dr. Ewert. I would have no idea how to do this, of actually showing the circuitry. Again, we're not guaranteed convergence. So you see here on the right are the highest level of fitness. We have the NOR function here in the upper right. And so that's good. And additional mutations, keep that NOR there. Hopefully it's not destroyed. It's kind of ratcheted into where it's supposed to go. Okay, this doesn't look like it's doing anything. We're up to 2 million queries right now. That's a little bit too much. So it looks like this one is not converging. These algorithms are kind of set up like a pinball machine. If you've ever played the pinball machine with the little steel ball, you pop it up and it starts bouncing around, and you use the flippers, and the flippers launch the ball back into the arena, and you get more bouncing around. And it's but eventually what happens? What happens is that the ball goes down the little hole behind the flippers, right? That's the way these algorithms are structured. Yeah, they go different ways, but that's there we found it. Okay, so about 3 million queries and 2,997 generations. What is a generation? Generation is kill off the weak, repopulate and mutate, and then repeat that again and again and again. So it did find it. So the ball fell behind the hole, behind the flippers, and we did get the NAND. Now, here's what's interesting. We can actually change these, and we can change the results here and actually find out what the effective is. But this is fine tuning. They chose this because it worked. So this was designed. They designed this in order to make their algorithm work. And if we assign different values, we would get a different result. If we made all of these zero, except for the EQU, that was what in the original paper they said didn't work, because the only success is when we got the EQU. Now, here's something interesting that Dr. Ewert found out. He found out that we didn't need all the instructions, that actually this problem that we're looking at is incredibly simple, and that we can actually go down and we can get rid of a lot of the things which screw up the evolution and look at so-called the minimal instructions. So the minimal instructions are these 5 different operations. And if we do these 5 different operations, we get we get an incredible result. So let's look at the simulation here. We're going to reset and we're going to redo it in terms of these minimal instructions. And we'll find out that's all we need to get the NAND. There it is. Do you see how quickly it did it? It did in 49 generations. There it did it in 34 generations. There it did it in 56 generations. So you can see instead of the millions of iterations, we just required a few. So it did turn out, and I don't think the original people knew about this, that all of these instructions that they gave were actually obfuscating the performance of their algorithm. And that if we choose them all, this was a heck of a lot worse, because these were a lot of bumps in the road that kept the algorithm from converging. And that's kind of cool. So there's other things that you could do here with MiniVita. And here's a description. This is on evoinfo.org. So let's go back to MiniVita, evoinfo.org, and we see that we are able to look at the dynamics of a Vita and see that it isn't such a big deal. Now, in terms of the computer program, we've talked about this before, but I want to emphasize it. Does quantum computing help? No, quantum computing does not help. Quantum computing reduces the search time by about a square root. So it turns out that, yeah, you still, if you have 10 to the 50th for a non-quantum computer, that means you have what? 10 to the 25th for a quantum computer queries. So that's still a heck of a lot. And that doesn't help a lot. So in conclusion, evolutionary computing is not equal to Schaeffer's perpetual motion machine for information. You remember from the no free lunch theorem, this was something that Colin Schaeffer talked about. I talked to Colin Schaeffer and he says, yeah, he recognized this immediately. And he says a lot of his colleagues did also. So the idea of an evolutionary computer of solving all the problems of mankind is not possible unless you fold in domain expertise and put active information into what's going on. Active information can be measured analytically or through simulation. In other words, we can go through and actually measure in terms of the number of bits that the domain expertise has been added to the search. Active information is needed. The multiverse is not big enough to explain the design we see. We saw that even if we had a multiverse with 10 to the thousandth different parallel universes, that still would not be enough to execute a blind search, a search without domain expertise. And then what is the source of active information? It is intelligence. So if we do have a random search that works, it's because of intelligence. It's because of the domain expertise. And I'm happy to say, after our publication of these two papers, that I'm aware of no more papers purporting computer simulation of Darwinian evolution. We had a big back and forth with Schneider, and finally everybody on his side said that we were right, and so I'm excited about that. And so we've had no more papers purporting computer simulation of Darwinian evolution. I don't monitor this as much as I should, so if you find something, let me know. That would be kind of cool. So here is the evoinfo.org place and a place you can go for evolutionary informatics. There is a video short course on evolutionary informatics at discoveryu.org that's taught by yours truly. And if you're interested in that, it costs, I think, $100 or something. You're certainly welcome to take it. I hope that was interesting for you. But the no free lunch theorem was a big theorem, and it kind of derailed everybody that was trying to show that their algorithm was better than somebody else's algorithm. The answer, according to the no free lunch theorem, is that indeed that you can't say that, because if a search algorithm works better on problem A, if the search A works better on problem A than search B works on problem A, then it turns out, well, problem A works better for search in problem A. So you can't say about how well it does in other cases. Thank you. That's all we have for today. Bye-bye.